Hello, and welcome back to Introduction to Algorithms. Last time we already announced today's topic. Today's topic is algorithms for computing the median of a given collection of data without sorting that data, and the generalization of median, calculating order statistics. So let me remind you of median and order statistics. So the problem with median is input a sequence of elements from a totally ordered set, and the goal is to calculate, well, first let's consider the problem of calculating the mean, the average. That's kind of easier problem, right? You just add all elements and then divide by the number of elements. So there's an easy, straightforward algorithm for calculating the average, the mean in linear time, and linear time is optimal because any algorithm calculating the mean must, of course, at least look at every element. So calculating the mean is not a challenging problem from the perspective of algorithm design. The median, however, is defined differently. The median is an element from the sequence or an index into the sequence such that roughly half the elements are smaller than that element and roughly half the elements are larger than that element. And observe that if this input sequence is already sorted, then there's not much to do here, right? Then just take the element in the middle of the array, and that's going to be the median. But here we want to devise algorithms that calculate the median without the hypothesis that the array is already sorted. Of course, as we will see in chapter 3, sorting takes n log n, and that's optimal. So our goal is to find an algorithm for calculating the median that beats the n log n lower bound, that avoids sorting and still collects the median in linear time. And that's actually what we're going to see today. This is, I'm going to say, one of the highlights of algorithm design, and it's on purpose. It is presented towards the end, towards the last part of chapter 2, because as you recall, we deliberately start very easy in each chapter and then gradually grow in difficulty. So this is where things start to get difficult. I also need to mention maybe the mode. The mode is an element which occurs most frequently if elements occur repeatedly. We're not going to talk much about the mode in this chapter. So let's focus on the median and its generalization. So the median is the element, the index, which has roughly half as many elements smaller and roughly half as many elements larger. So that means n over 2 elements plus minus 1 are smaller than the median, and n over 2 elements are larger. And the generalization is that find an element which has k elements smaller and n minus k elements larger. And this is called the kth order statistics. So choosing k equal n over 2 recovers the median, but other values of k generalize the median. So that's a generalized generalization of the median problem. So the input is not just this finite sequence unsorted, but also integer k. And the goal is to output an index for the kth order statistic. And the precise specification, recall our virtues, the precise specification says that the output should be an index m, such that the number of elements smaller than the mth element is roughly k. And with roughly, I here mean there are some subtleties if they are repeated elements or if the elements are omitted from the sequence. So the precise specification says that the number of elements smaller should be smaller than k, and the number of elements smaller or equal should be greater or equal to k. And I want to make it an exercise, an assignment, or maybe a quiz that you formally prove that this specification is well defined. Recall, we've spent a lot of time in the first chapter pointing out the importance of a rigorous, of an unambiguous, of a total specification. And I would like to have you verify that such an element, such an index M, indeed always exists and it's unique, because, and that's the reason why we spend so much effort on this subtle and complicated specification for the kth order statistic problem. So now the problem is well specified, and also which operations we're going to use is straightforward. We use, as usual, indirect access into the array at unit cost, and we use ordered comparison. So that's the problem specification. And as I already said, there's a trivial algorithm for calculating the the median and the order statistics by simply trying all possible candidates for that index M. So this is this outer loop, and in the inner loop, count the left side and count the right side using this loop. So small a is going to count the left side of this inequality, the number of indices which of elements which are strictly less. That's what you see here. If the element at xn is strictly less, then increase the count a. If the element is less or equal, then increase the count b. And at the end of calculating both these counters, both the left and right hand side, check whether this choice of M satisfies the condition of the specification, and if so, then return that index, and if we're done, then we're done. Otherwise, try again with the next candidate index. So that's a trivial algorithm based on the specification. It uses two nested loops and therefore has quadratic running time. And as I emphasize, that's what we want to beat. We want to try to devise a more efficient algorithm, subquadratic time algorithm. And if the array is already sorted, then again, the problem becomes trivial, because then the element at position k is, by its very definition, the kth order statistic, right? If the elements are already sorted in non-decreasing order here, then obviously the element at position k satisfies this condition. So that's a constant time algorithm, but using the condition that the input data already is sorted. And as we're going to see in chapter 3, we can sort an array, we can sort the elements in time n log n, and this is optimal. One cannot do better than n log n for sorting. This is also something we're going to prove in chapter 3 rigorously. But here we want to kind of beat that and find an algorithm for calculating the median and more generally the kth order statistics in time O of n, in linear time, without the hypothesis of previously sorting. And obviously, in order to do that, we cannot sort, because that's going to take n log n necessarily. And this is where we're heading now, highlight of chapter 3, searching. So no, not in chapter 3, but in chapter 2 right now, linear time median algorithm. And the linear time median algorithm we're going to learn first calculates an approximate median, an approximation to the median. And what do I mean with that? I mean the the algorithm we're now first devising before proceeding to the linear time medium will output an index m such that the number of elements smaller is somewhere between 30% and 70%. So it's not a real median. Median should have 50% smaller, it's 50% larger, plus minus 1. But here, this algorithm will find an index which has 30%, between 30 and between 70% smaller, and vice versa, between 70% and 30% larger. So you see the problem specification for this approximate median problem is deliberately designed symmetric, right? So this is between 30 and 70% smaller or equal, and thus by contraposition, between 70 and 30% will be larger. Okay, so that's the specification of the problem we want to solve first algorithmically. And to do that, let's do some little combinatorial analysis, some double counting, and suppose we partition the input data into groups of 5. So here is a group of 5. Here's the next group of 5, all groups of 5. And as usual, it's no loss of generality to suppose that the total number of elements n is divisible by 5. If it's not, then we can just add some dummy element. That's, I'm not going to expand on that further. So no loss of generality, that dividing the input data into groups of 5 is always feasible. And that's what we do here. And now imagine that we calculate the median of each of these groups of 5 individually. So calculate the median of these 5, maybe even sort these 5. Since 5 is a constant number, it doesn't really matter asymptotically whether we sort them or use some other means. It's a finite problem. So there's an algorithm which calculates the median of these 5. And we invoke that algorithm also to these 5 and these 5 and these 5 and these 5. And let's suppose that the black dots represent the median of these 5. This black dot represents the median of these 5, and so on. So what we're seeing here is already basically a recursive algorithm, right? Namely, in the next step, we only look at these black dots. The black dots, these are now only 20% of the data we had initially, right? So initially we had this 5 and this 5, and this was comprised the overall data. And now we have identified the median of these 5, median of these 5, and now we're going only to look at these medians, which now only make 20% of the size of the initial data. And now we recursively calculate the median of these black box recursively. That's the algorithm. And I'm going to present the algorithm in pseudocode on the next slide. But what we want to do here is to make an analysis of the properties of this median of 5 medians. And for the purpose of this analysis, let's suppose that the medians are already sorted. This is not what we're going to do algorithmically, but for the purpose of analysis, let us do that. Let us suppose that these black dots, the medians of these 5 medians, are sorted in non-decreasing order, meaning that all these medians are less or equal to the median of 5 median, and these are greater or equal to the median of 5 median. And let's analyze the combinatorial properties, quantitative combinatorial properties of this median of 5 median. So this is actually a technical term. This element is called the median of 5 medians. These are the 5 medians. This is a 5 median. This is a 5 median. And all these 5 medians, we calculate the median of these 5 medians. And the premise that this is less or equal to at least half of 3/5 which amounts to 30% of the overall number of entries. Let me say that again. This median of 5 medians, we want to prove that this is indeed an approximate median in the sense of the specification, and thus an algorithm which calculates the median of 5 median will produce an output index M with the required approximate median properties. That's what we claim, and the lemma says this is indeed true. Now let's see why this is true. Why is this true? Well, look at this red, the elements in this red circle, right? So first, these two elements are greater or equal than the median of 5 medians, because this is a median of these 5 medians, which means that these two elements are larger or equal, and these are smaller or equal. That's a defining property of being a median of these 5 elements. Same here. These elements are larger or equal than this, but also this median of these 5 elements is larger or equal than this median, because, as you recall, here we have calculated this being the median of 5 medians means that these medians are larger or equal than this one, and these medians are smaller or equal than this one. So that means this one is larger or equal than this. And by transitivity, that's where we have a total order. Also, these two are larger or equal than this. And the same here. This median is larger or equal than this. And these two are larger or equal than the median. Therefore, all these are larger or equal than the median of 5 median, and so on. So that means all the elements in the red circle are greater or equal than the median of 5 medians we have just calculated. And now that's at least these, right? We cannot say much about these elements, right? This median of 5 median is larger or equal than this one, but these elements are smaller or equal than this, and there's no way of telling whether they're larger or equal than this one. This is completely undetermined. We cannot say anything about this. We cannot say anything about these, but we can say that these elements are all larger than this one, larger or equal. And how many of them are there? Well, there's 3/5 elements in each of these groups, right? 3/5 elements in this group, 3/5 elements in this group, 3/5 fraction of elements in this group. That's the fraction of elements. And how many groups are there? There are at least half of the groups are larger or equal than the median of the 5 median. That's the factor of 2. So let me say it again. We look at all these groups, and at least half of the groups have medians which are larger or equal than the median of 5 medians our algorithm will have calculated. And out of these 50% of the groups, 3/2 fraction of the elements are larger or equal than their respective median, and thus by transitivity larger or equal than this median of medians. So that in total, a fraction of half of 3/5 of the total number of elements is larger or equal than the median of 5 medians. And that's by calculation is at least 30% of the elements. And that's a requirement here, right? That's exactly the condition, the number of elements that is, oh, we're going to get there in a minute. Because now let's look at the contraposition. That means by contraposition that at most 70% of the elements must be strictly larger, right? That's the remaining elements. There cannot be more than 70% can be larger. Namely these ones and these ones and these ones. That's at most, as could be less, but at most that many elements. And now we're going to repeat the same argument with comparison reversed. And we were going to look at these elements. These elements, I'm going to claim, are greater or equal. No, it's the opposite. These elements are less or equal, and these elements are greater or equal. So the baseline is at least 30% of the elements are also greater or equal. So And this is exactly the specification here that we want to satisfy. How many elements are less or equal than the median? That's at least 30% and at most 70%, plus minus 1 because of rounding, integer rounding. And similarly for the other part, at least 30% are less or equal, and at least 30% are larger or equal, meaning at most 70% are strictly greater, and at most 70% are strictly less. That's our analysis of the median of 5 medians. And now we're going to design an algorithm and analyze an algorithm that calculates these median of 5 medians, right? And that's solve the approximate median problem. And this is an algorithm. The function approximate median receives as input the array that we want to, in which we want to calculate the approximate median, and actually not in the entire array, but only in a subarray from position index L to position index R. So from L to R, that's a subarray. Okay. And the algorithm, based on the analysis we just saw, partitions the input array into groups of 5, and then sorts each one to find its median. That's what we just saw in the previous picture. And then it calculates the median of these 5 medians. How does it calculate the median of these 5 medians? By making a call to the algorithm median, or more general, the algorithm order statistic, which calculates the order statistics of a given array. Okay. How do we calculate the median or order statistics of an array? Now, not approximately, but now rigorously. Here's an algorithm that calculates the median and more generally the order statistics precisely, not approximately. And this algorithm is used by approximate median. Here is the algorithm. Again, the input is an input array, left and right position, and it receives as input a parameter k, for which order statistics it just calculate. And the algorithm uses a loop to calculate the approximate median. So it now calls this algorithm we just designed to calculate an approximate median of this array. Okay. And then uses the approximate median to split the array, to put all elements that are less than the approximate median to the left of the array, and all that are greater to the right of the median. So we don't sort. That's a very important observation. We don't sort, but here we put all elements that are smaller than the median, approximate median, to the left half of the array, not half actually, and all that are greater to the right part of the array, right of the median. And I'm going to show you the algorithm that does that on the next slide, but let's now just suppose we have that algorithm and call it here. And then let's look at how many elements are smaller and how many elements are larger. If the number of elements that are smaller are less than half of the elements, then that means that the median is located in the right part. And if the number of elements that are smaller are greater than the median, greater than n over 2, then that means that the median must be located in the left half. Or more generally, if the number of elements that are in the left part is greater than k, the kth order statistics, then the kth order statistics is located in the left part. And if the number of elements in the left part is smaller than k, then that means that the kth order statistic is located in the right part. So, and this is what happens here. And it involves decreasing thus the right and the right index of the subarray we are looking at, or increasing the left index of the subarray we're looking at accordingly, depending on where we should proceed now in the next iteration of that loop. And that loop continues as long as the left subinterval is greater than the right subinterval. Once they become equal, then we have really identified a single element, and that's going to be our median, or more generally, our order statistic. So this is our algorithm for calculating the median. I have to point out, this is really what makes this so special an algorithm, because there are basically two algorithms that recursively call each other, right? So there's this one that calculates an approximate median, not precise, but also only median, not an order statistic. And that makes a call to order statistics. Order statistics to calculate the median of these 5 medians. Order statistics in turn makes repeated calls to approximate median here, as you see that. So they mutually call each other repeatedly, recursively. And now we need to analyze, well, the correctness is thus by design, right? And by the lemma we proved on the previous slide. And now we need to analyze the running time, and also to make sure that the two algorithms do terminate. And I still owe you the algorithm for splitting. Okay. So yeah, let's talk about that. Right. So what is the running time of these combined algorithm? So let's denote by n the length of the subarray we're currently processing. The length of the subarray we're currently processing is the right index minus the left index plus 1. Okay, that's our n. And I'm going to argue that the algorithm, both algorithms actually, calling each other recursively, repeatedly, have a running time which is linear in that number n. Okay. And to this end, let's analyze the first algorithm. The running time t incurred by the algorithm approximate median on input arrays of length n is, first there's a linear part. Where's the linear part? The linear part comes from partitioning the input array into groups of 5. Then it makes a recursive call to the order statistics, right? Here, this is a recursive call to order statistics, but now it makes a recursive call to order statistics only to the 5 medians. So remember, from these groups of 5 elements, only one element gets picked here. That's also part of the linear time, right? Sort each of these groups of 5. There are a linear number of groups of 5. Each one incurs constant time for sorting, so that the running time of this is linear. I need to emphasize that one more time because it's so subtle but important. We don't sort the entire element. We sort each group of 5. Sorting a group of 5 takes constant time because 5 is a constant, and there are a linear number of these groups of 5, so that this linear time comes from sorting each one individually. Okay, that's not sorting all of them. And then taking these 5 medians, of which there are 20%, right? 20% of the original data remains by picking only these 5 medians, collecting these into a separate area or whatever, and then making a call to this order statistics, now with only 20% size of the initial data. So that's our analysis of the first algorithm. Now we also need to analyze the second algorithm, right? Because it gets called here. What is the cost of the second algorithm? Well, the second algorithm makes a recursive call to approximate median. So the running time here incurred is the running time of the approximate median plus some overhead for splitting, which I still owe you the algorithm for that. linear time for splitting, as we will see, plus there's a overhead for the now repeating the same again with order statistics, because in the next iteration, as you recall, the number of elements that are smaller and the number of elements that are larger are at most 70% of the elements that we had previously. So we only proceed in one of the two subarrays after splitting, and by our analysis from the previous level, whichever subarray we proceed to in the next iteration is going to be 70%, at most 70% the size of the previous one. So that's our analysis of the, and that also shows why this loop terminates, right? This loop terminates because in each iteration of the loop, the length of the subarray r minus l plus 1 decreases at least by 30%. It is at most 70% of the previous size. So this loop gets executed at most a logarithmic number of times. Yeah, this is now a combined recurrence. Observe that since the two algorithms call each other mutually recursively, that means you also have a combined recurrence, one algorithm calling the other, incurring this cost, and the other calling the first one, incurring this cost. And so by combining these two recurrences, right? So plugging here in T of A, right? We arrive at this recurrence, right? TO of n is linear plus TO of 70% plus TO of 20%, that's TO of 90%. So that's a recurrence for the simplified combined recurrence, like in linear algebra, combining two linear equations to eliminate one variable. Here we combine two recurrences to eliminate one term. And this recurrence we can solve using the master theorem and see that the recurrence, the solution is linear. It's linear time incurred by order statistic, and thus, since approximate median, plug that in here, right? Now plug in the solution in as a linear algebra. That's 20% of linear is still linear, plus linear is still linear. That means also the first algorithm has linear running time in combination. And that's the famous linear time algorithm for calculating the median and more generally for calculating order statistics. We can start calling the algorithm which one we want, because they will then proceed to recursively call each other mutually. So that's, did I emphasize that this is really a highlight of chapter 2, searching a linear time algorithm for median. And just to wrap things up, I still owe you and will now present the linear time algorithm for splitting that, but that's kind of boring. So here it is, the algorithm for splitting. Remember the specification of that algorithm. It receives as input an array and indices of the subarray and element where to split at. And it will put all entries which are smaller than that element into a left part, and all that are greater or equal into the right part. And then we'll return where the left part ends and where the right part begins, because that's not fixed a priori, right? So if y is very small, then that means the number of elements smaller than y could be very few, and the number of elements larger than y could be very large, and vice versa. It really depends on y, where the split is going to happen in terms of indices, right? Because the split is happening in terms of the values, and where the split happens in terms of indices is part of the result of the splitting process. And with that specification, it's easy to see what how the algorithm proceeds. Takes the left and right part, and while these parts are non-empty. It compares the current element to the y, which we're given. If that is left, then it already is left and there's nothing to do, and we increase the, we kind of leave that in the left part and increase the index. If it is greater or equal, then we decrease the right part, and otherwise, if the two entries are in the wrong position, we swap them. So we swap put x of a into x of b and put x of b into x of a. And that's a simple algorithm, right? So it kind of moves on from both ends, right, left and right. And if the elements are already in the right position, not with respect to sorting, but with respect to this splitting, then they just proceed, either increase the left position or decrease the right position. And otherwise, if they're at the wrong position, then they're being swapped, and that's it. And this is obviously a linear time algorithm, because in each iteration, there's only one loop, and in each iteration of the loop, at least one of the two indices, A and B, get incremented or decremented, and thus after a linear number of iterations, A meets B. So that's a kind of algorithm, linear time algorithm for splitting, and thus we really finally have finished our complicated but very interesting algorithm for calculating medians, and more generally for calculating order statistics in linear time. So let's now take a short break where we answer your questions. Welcome back after this short break, and thank you very much for your excellent questions, which I'm happy to take the opportunity to answer and thus explain more this indeed a sophisticated algorithm. So this is very justified that you're asking this question. And so let's recall the first algorithm is the approximate median. Yes, so your questions pertain to the second algorithm. Approximate median makes calls to order statistics, and order statistics calculates the kth order statistics with a parameter k, where the call here for approximate median means that k is equal to n over 2 here. And order statistics recursively calls approximate median to determine the approximate median m of these elements. And what do I mean by that? Right, so that means an index according to our specification of the exact median to split the number of elements in the array. And with splitting here, I mean that all elements that are less than the element at the median position are put to the collected at the left interval sub-array, and those that are greater are collected to the right. And where exactly these arrive at, that of course depends on the choice or the value, right? That's the whole point. That's a difference. What makes a difference between median and average, right? So if the median is a small, then that means that right, by the choice of the median, half of the elements are put to the left and half of the elements are put to the right. And where the split is going to happen, that's what the return value of the splitting function that I introduced before the break, but I'm happy to recall that. So that's a recursive call here. And let's see whether we can, right. Yes, and after this splitting, then that means in the next round of the order statistic algorithm, the algorithm can focus on only one part of the two subintervals, right? So since it's an approximate median, not an exact median, that means the number of elements in the left part would be something between 30 and 70% of the original number. And those in the right part of the interval would be something between 70 and 30% of the original ones. And in the next iteration of this loop, order statistics can focus only one of the two parts, namely if the proceed either to the left or proceed to the right, according to where the kth order statistic is going to be in. Let me make that more precise. So if k, the order statistics we're looking at, is less than m minus l, that means the number of elements in the left part, right? So the left part starts with L. If the number of elements in the left part is smaller, is greater than K, then that means that the kth order statistics is going to be in that left part. Whereas if K is larger than the number of elements in the left part, then that means the kth order statistic is going to be in the right part. And being in the left part means we can now reduce the right bound of the interval to m. That's where the split has happened, right? And if the case order statistics is in the right part, then that means we can increase L, the left bound of the interval, and focus on the right part of the interval. And in the latter case, we also need to decrease K, because now we've discarded already many elements that are smaller, and thus K needs to be decreased by this very value. So this is a mutually recursive calls of the two algorithms, right? And there were no questions pertaining to the analysis, which is indeed original and intriguing. Right, there was, however, a very good question of why do we calculate median of 5 medians, right? So here we are, right? So in this picture, we choose medians of 5 medians. Why do we choose medians of 5 medians? Why not medians of 4 medians, or median of 3 medians, or medians of 6 medians, or median of 7 medians? Why this particular number of 5? And this is such a good question that it will probably occur somewhere, maybe as a homework, or maybe even in the exam. So please hold that question, think about it, repeat the analysis. You really learn a lot, not by just listening to me explaining, but by performing the analysis yourself, and repeat the analysis with a different value. Replace 5 with some different constant and see what happens. Excellent question. Okay, so now we've really finished, completed our algorithm for calculating linear time medians, and more generally linear time calculating order statistics. And now we move on to the last part of chapter 2, searching, namely geometric search problems. Okay, so yes, here we want to talk about range counting. And in range counting, we start first to the one-dimensional case, and then we move on to 2-dimension and 3-dimension, thus generalizing it. So first, the problem specification. One-dimensional range counting is the following problem. We receive, as usual, finite sequence and 2 inputs, x smaller than x prime. And we want to report how many elements are in this range between x and x prime, that is, have value strictly greater than x and less or equal to the x prime. So it's a half of an interval. And right, this algorithm is naive, right? So it simply walks through the interval and counts all elements that satisfy this condition. And if they do, then it increases the count. That's a linear time algorithm. But can we do better if we can suppose that the array is sorted. So let's now add the additional hypothesis that the array is sorted. If it is sorted, then we can use binary search. We call the specification of binary search. And binary search returns an index, which is kind of close of an element which at the position where y would or should be in the sorted array. And now we can use that in our much more efficient algorithm under the hypothesis that the data is sorted. Namely, we first locate the left element position in the array. We locate the position of the right element in the array, and then we calculate simply the difference between both, because the difference between both, that's the length, that's the number of elements between of value between x and x prime. So that's a linear logarithmic time algorithm because it makes two calls to binary search, and binary search has logarithmic running time if the original data already is sorted. So that's kind of easy, but now we want to move on to higher dimension. We want to solve the two-dimensional range counting problem. And before I do that, let me introduce to you a different algorithm that solves the one-dimensional range counting problem. So we already have solved the one-dimensional range counting problem, and this algorithm is already optimal, but this algorithm does not generalize to higher dimension. I still owe you the specification of the higher dimensional version. So before proceeding to higher dimension problem specification, let's look again at the one-dimensional range counting problem as specified here, and look at a different algorithm that solves that problem also in optimal logarithmic time, but in a different way, in a way that then does generalize to higher dimensions. So here's a one-dimensional range counting problem revisited, and here we use a search tree data structure instead of a sorted array. The search tree data structure, let me illustrate that with an example. So you know, of course, a tree data structure and binary tree and search tree from your course on data structures. And here you see such an example of a tree where, again, using the hypothesis that the data is sorted, this data is now in the leaves of this somehow balanced binary tree. So it's a binary tree, as you see here, and it's a balance in the sense that it has logarithmic depth. And how to construct such a tree is a different question that is deferred to either data structures or to chapter 3, actually. But for now, we take such a tree for granted. And now we cannot simply take, well, we can find, again, since it's search tree, we can find x prime here and x double prime here, but we cannot simply take the difference because this is not an array, right? The leaves here are not generally located in an array. Instead, we enhance the search tree. In the internal nodes, we store the smallest element in its subtree. Here in this example, it is 6. The largest element in its subtree, here in this trivial example, it's 8. And the number of elements in the subtree, here it is 2. And we do that for every internal node. You see that here, for example, the smallest element in that subtree is 1, the largest element is 17, and the number of elements in that subtree is the number of elements here. And this is, we do that in, and again, we don't delve here into the question how to construct such a tree. So the so-called pre-processing part of this algorithm is deferred to chapter 3, sorting. So now, taking that for granted, we have a different algorithm for solving the one-dimensional range counting problem as follows. So let's suppose we are asked to calculate the number of elements in the range from x prime to x double prime. For example, if x prime is 7 and x double prime is 41. Then we can use the search tree data structure to locate 7 in this tree. So looking at the left child of the root, we see that the left child represents ranges from 1 to 17. The one we're looking for, 7, is in that range, so we proceed into the left subtree and don't worry about the right subtree anymore, because the range here starts with 26, which excludes the one we're looking for. Then we repeat the same, look at the 2 children. This one represents ranges from 1 to 8, which includes the one we're looking for. This one excludes the range we're looking for, thus proceed to the left one. Okay, so that's happening here. And then we do that again. Left subtree is trivial, does not include the value. Right subtree is non-trivial, it includes the value, so we proceed here. And then we find that the value we're looking for is somewhere in between, so we know we need to start looking here. And now we do the same again with the right bound of the interval we're looking for, 41. 41 means we proceed to the right subtree. 41 means we proceed now to this subtree, not this one. And 41 means now we proceed here, and then we're done. Okay. Now, having thus located the left interval bound and the right interval bound, how do we calculate the number of elements here? Now, to this end, we now move up. So first we see that this node is in the range. So we count 1. Then we move up and see that this range, right? So bottom up the recursion, see that this range is entirely contained in the range we're looking for, right? That's why we didn't proceed into this part, but into this part. So that means the range from 12 to 17 is entirely contained here. So we add to our previous counter, which already stored 1 element here. We add this number, which is already preprocessed stored in the internal node, 3 here, thus representing all these 3 elements in one step only. Okay. And then we proceed to the right subtree. Here we've ignored that. We went here, and then we went here, which means that this subtree is entirely contained in our range, 2 elements. So we add 2 elements, which again are already stored in pre-processing, but not spelled out here. And then this 1 element. So that's our algorithm, illustrated with an example. So we proceed down, locate the left interval bound. We proceed down a second time, locate the right subinterval. And then we collect all internal nodes on the path downwards that we skipped, because the range left interval bound would not intersect them. And since the left interval bound does not intersect them, it means that these ranges are entirely contained in the interval. And then we only need to add the number that is already stored in the node, representing possibly many elements to our counter. And since our algorithm moves down twice and then moves back up here and moves back up here, and in each on each level it adds the numbers stored in that level, that means that the running time of this algorithm is also logarithmic. So let me say that again. Here are the ranges that of the internal nodes that are entirely contained here, and this is this one and this one and this one and this one, and the algorithm identifies these nodes while proceeding downwards. These are the nodes that are kind of on the boundary of the interval, left boundary and right boundary. And then when we're moving up, it adds the counts that are stored in these internal nodes. And how these internal nodes are initialized is different. And so the algorithm moves down twice and moves up twice, once for the left and once for the right. The tree has logarithmic depth, and therefore the algorithm has logarithmic running time. That's here. And also the memory is still linear. In our previous slide, in our previous algorithm, that was obvious because it used an array, and the array has linear memory. But also here, this tree has linear memory, because as you see here, every internal node only stores a constant amount of information. The left, the smallest element, the largest element, and the number of elements in the subtree. So that's 3 numbers in each internal node. And as you know, the number of leaves in a binary tree is at most twice the number of internal nodes, at most as large as the number of internal nodes. Therefore, the number of internal nodes is also linear and constant information in each internal node. So that's a different algorithm for solving the one-dimensional range counting problem. The point that I want to emphasize again, the algorithm does not walk along the leaves, right? Walking along the leaves would not result in a bounded time algorithm, because the range, the number of elements in the range could be very large, right? Much larger than log m. It could be all elements could be in the range if the range is very large, right? So looking at each element in the range is prohibitive for a logarithmic time or even a bounded time algorithm, a sublinear time algorithm. That's a trivial algorithm we started with previously, right? And this algorithm beats that by counting, by adding large numbers in one step if all the subtree here is contained in the range. That's our search tree algorithm for the one-dimensional range counting problem. And the reason we introduced it is because that one generalizes to 2 dimensions. But first, I need to specify the 2-dimensional version of the problem. So here's the 1-dimensional version for your memory. And the 2-dimensional version considers not a finite sequence of elements in that totally ordered set, but it considers 2 totally ordered sets and their Cartesian product. And the Cartesian product of 2 total orders is in general not a total order, right? Yeah, that's like the plane, real geometric plane, or complex numbers are not totally ordered. And so thus the input here also consists now not of elements from the totally ordered set X, but pairs of elements from the Cartesian product of both totally ordered sets. And also 2 bounds, X prime, Y prime, a pair, and X double prime, Y double prime, another pair. And the output, according to the specification, is now not the number of elements that satisfies the X range condition, but the number of elements that satisfy both conditions component-wise. That here means component-wise. That means we're looking at the number of elements whose X coordinates lie in the X range and whose Y coordinates lie in the Y range. So it's a conjunction of 2 total order conditions. And geometrically, we can imagine that by having, right, so here is the kind of Y conditions, here the X condition, and geometrically this means that the elements we're looking for lie in some kind of rectangular range, right? And to emphasize that again, we cannot simply look at all elements that satisfy the X condition and then filter those that additionally satisfy the Y condition, because that could be very large a number of those which satisfy the X condition, but not the Y condition, and so on. So that trivial algorithm is prohibitive from the perspective of efficiency when we want to beat and get lower than linear time. So how do we proceed here in this case? That's where our one-dimensional range tree, search tree comes in handy. So you still see here the one-dimensional search tree, now the one with respect to X coordinates, ignoring the Y coordinates for a moment. And recall that previously, every internal node would contain 3 information: the smallest element, the largest element, and the number of elements in the subtree. And that was the one-dimensional case. In the two-dimensional case, we generalize that and instead store in each internal node an array of all the elements in the subtree. Now this array is sorted with respect to the y-coordinates. So the naive algorithm, which you barely can see here, is first find all indices satisfying the x condition and then filter those with the y condition, but that is not a sublinear time algorithm. Instead, we store in each internal node a sorted array, sorted with respect to y coordinate, those elements that are in the subtree. So for example, this node represents this subtree. These elements, these are the x coordinates, but every element also has a y coordinate. And all these elements are stored with this again, repeated, stored again, sorted with respect to their y coordinates in this internal node. This node contains all these elements. Here you see the x coordinates, but they all have y coordinates, and stored in one array, all these elements sorted with respect to their y coordinates. And the thing to observe here is that now we introduce a memory overhead, because we know for the first time we store elements repeatedly. Now the information stored in each node is not constant anymore. It reflects number, it's the number of elements in the subtree. Also, this node stores element repeatedly, those in the smaller subtree. And this one stores all those elements in this subtree. So that means that elements occur repeatedly on each level again. So every element that occurs here also occurs in this array again, sorted array. All elements that are stored here occur again here. So we really have redundancy in terms of memory, but the redundancy is bounded because these two arrays are disjoint. This one contains all the element in this subtree, this contains all the element in this subtree, and that's it, right? So that means the number of elements stored in each level is linear. So here we store all elements repeatedly. Here we store all elements again repeatedly. Here we store all elements again repeatedly. So that means on each level we have linear memory. And since we have a balanced tree, that means the number of levels is logarithmic. So the memory overhead is n is logarithmic. So the overall memory is n log n, as opposed to the previous one-dimensional case where we had linear memory of n. So that's our data structure. And you see again here the ranges. And now again, I didn't tell you how to create such a tree, but with such a tree, we now can solve the two-dimensional range counting problem in sublinear time, again, by moving down with respect to the x coordinates as in the previous case. But now all the internal nodes, that's the one marked here with octagons here, with pentagons, these ranges, in each range, we now not simply add the number of elements, as in the previous case, but here we perform two binary search among these elements, among these arrays with respect to the y coordinates. Okay, and then count the number of elements that satisfy the y condition, in addition to they already know to satisfy the x condition because they have been identified when we walked around that tree. So we perform two binary searches here in this array with respect to the y coordinates. We perform two binary searches here, perform two binary searches here, and so on. So that means we have a logarithmic number of binary searches, logarithmic because that's the depth of that tree. And each binary search in turn takes logarithmic time for the binary, for the y coordinates, so that the running time is now logarithmic squared to solve the two-dimensional range problem. And now there's nothing stopping us from dimension 2 moving on to dimension 3. Here you see the picture. So now we have 3 sets, each with total orders. Input is a finite sequence of triples and 2 bounds. Output is the number of elements that satisfy these bounds component-wise. And now what we do, instead of using arrays for the y coordinates as internal nodes, we use one-dimensional range tree for the y coordinates here in each node, and in each internal node of the y tree, we use an array for the z coordinates. So let me say it again. We iterate these trees now. These are nested trees. So we have one tree with respect to the x coordinates. In each internal node, we now have a similar one-dimensional tree for the y coordinates, and each internal node of that tree, we have an array for the z coordinates. And I refrain and leave it to you to spell out the algorithm that deals with this 3-dimensional range counting problem. And just to observe that the memory overhead is now logarithmically squared, so n times log squared, and the running time is now logarithmically cubed. And you see, or you can imagine how that generalizes to 4 and higher dimensions. So here it's logarithm to the dth power, and here's logarithm to the d minus first power times n. So that is about the range counting problem, geometric range counting, rectangular range counting in arbitrary dimension. There's also variant count range searching, where we're not asking for the number of elements in that range, but for asking for the elements themselves. And obviously, if that number can be large, can be much larger than log m, so we cannot expect output or this algorithm to run in logarithmic or any sublinear time, but the time will always be at least as large as the number of elements returned, which we denoted by k in the previous slides. So, and this problem can also be solved with these range trees, and they are nested range trees using n log n memory and running time k plus n log n, where k now denotes what is called output sensitive running time, depending on how many elements are being reported. Okay, so this is to kind of a cross promotion to an entirely different lecture on computational geometry. This is kind of to give you a taste of the problems solved in considered in computational geometry and the algorithms used to solve them. There are many more such problems and many more such algorithms. Very nice area, and I highly recommend it. But for now, in this introductory course, let's wrap up chapter 2 about searching, and recall that we talked about linear search, we talked about neighbor search, we talked about binary search, we talked about the uniqueness problem, we talked about hashing as a means to solve your uniqueness problem, both in linear time and with linear memory, reducing the memory overhead of our previous algorithm, provided that the data we're processing consists of integers. We talked about median problem and its generalization, order statistics, and algorithms for solving that problem. First, trivial algorithm with linear running time and constant running time if the data is already sorted, and then a real highlight, a linear time algorithm for calculating median and order statistics using 2 algorithms that mutually call each other recursively using this median of 5 medians. And finally, we talked about range counting and range searching problems in various dimensions, all pertaining to the virtues of specification, primitives, design and analysis, and optimality. So that's all for chapter 2. And now I'm going to indicate what chapter 3 will be about. Second. In chapter 3, sorting, will talk about specification as usual of sorting problems. We'll just start easy with bubble sort, selection sort, insertion sort, merge sort, quick sort. Then we'll record the linear time median, because the quick sort, as you may know it, is not n log n running time, but quadratic running time, and only with the linear time median algorithm it will attain the famous n log n running time. We'll talk about algorithms that can sort in linear running time, and we'll prove that n log n for quicksort is actually optimal. And if that sounds like a contradiction to you, then congratulations, you've observed well, and we will resolve that contradiction in the next chapter.